of, in fact, he was head of Department of Physics, City College, University of Calcutta. But that is not everything. He is a very passionate science communicator. In fact, he is a very close associate, well-wisher of Field Industrial and Technological Museum. We really feel privileged to have him with us and to deliver a talk that is quite relevant to the celebration of Raman effect. You all know, you have been told a number of times on this day in the year 1928, Sir C.V. Raman made a public announcement of his discovery. So he will talk about light illuminates, and the study of light enlightens. So I welcome you, sir. So all the best. Enjoy the day. Thank you.
Thank you, sir. Thank you very much. I'm really not going to elaborate on anything more. I'll stay here going to go to my presentation. There is some problem with my voice, but I shall try to be as distinct as possible. So, as you have already seen, the title of my presentation is Light Illuminates and the Study of Light Enlightens. All of us know that light does illuminate, but there is something more. I mean, a lot of things get revealed once we make the study of the light. Now, as you know, I mean, we have to start with this. This is the photograph of Sir C.V. Raman, which is a very famous spectrograph. He actually used this spectrograph to discover a particular phenomenon involving light that goes by his name, Raman effect. And all of us know in 1930, this happened on 28 February 1928, right in the city in Calcutta at that time. Now it's Calcutta. It happened in the laboratories of the Indian Association for the Cultivation of Science. That happens to be probably the oldest research institute in Asia, and of course the oldest research institute in India. Now, you see, Raman was awarded the Physics Nobel Prize for this discovery of Raman effect in 1930, and he was the first one. After Rabindranath Tagore, he was the Indian to get a Nobel Prize, but he still remains only Indian to receive a Nobel Prize in Science while working in India. We do have very great luminaries who have obtained Indian origin, but they have really done their work elsewhere and got Nobel Prize. So Raman is still very special. It's nearly 95 years. Now, this is, can you put this lights on? These lights. These lights? Yes. Can you Now, this is an interesting photograph. This is what is known as composite satellite photograph. What do you mean by composite satellite photograph? You can understand if the satellite takes the photograph from the space, half of the globe will be illuminated where the sun rays are falling, and half of the globe will be dark. Basically, it has taken two different photographs and they have been put together. And you can see that the distribution of light, how it really, see, this is the North America, mainly US and part of Canada, it is quite illuminated. But if you look at South America, only the coastal parts are illuminated, the central region is not illuminated. And Africa, well, the scenario is not that good. Only in South Africa we find some illumination. But if you look at Western Europe, that's quite illuminated. And our country is reasonably good in that regard. In Japan is fully illuminated, and there is China, part of Eastern China that is illuminated, and there is Singapore over here. And in Australia also you can find the coastal regions are illuminated. This essentially indicates that the light, if we can use, I mean, if a nation can use light to illuminate the dark night in its own territory, it's a good thing for them, and it's a good thing for its citizens. And this has happened in some of the places and not all over the world. And this is why that way is very interesting. And you just think about it. if, I mean, depending on the habitation, this part is not, sorry, this part is not very, this part is not very habited. So this part is dark, understandable. This part is also not very habited. But there are many parts, and this part is a northern region, so Arctic region, you can understand why we should expect light at certain places. But still, as you can see, we need more light to illuminate more parts of the globe. Now, when you talk about light, you can understand basically our main source of light and heat, of course, is the sun. But basically, we need these two things. I mean, the light and heat for the survival. And I hope all of you will appreciate that long time back, when people in ancient civilization, they could first make their fire artificially by striking suitable stones. Then it was a great achievement for humankind. And we are having, we got light and we got both heat. And as you can understand, the sunlight is available only 50% of the time. The rest of the 50% you will have to have other sources of light and heat, other sources of energy to start with. I mean, electricity and other things came much, much later. Now, so both light and heat, these are necessary. So, now, if you really look at it, that now, when sun rays are there, what happens with the sun rays? As you can see, this is the globe. Sun rays are coming from this side, from the left hand side. They very interestingly, whatever sun rays fall on the globe, in the polar region, the absorption of light ray is much smaller, as it is expected. There is large ice sheets and light gets reflected from there, so they don't heat up, so to speak. In both the polar regions, Arctic and Antarctic region, and Antarctic region. But if you really look at this portion, central part, between the Tropic of Cancer and Tropic of Capricorn, there is a lot of heat that is coming and those are getting absorbed. So these parts are warmer, so to speak. And ultimately, I mean, if we can make use of the sunlight, sun rays, that always helps us. Now, you will find that that's why we talk about positive heat balance at the tropics. By positive heat balance, we mean whatever heat is coming, there is reflection, but much lesser part is getting reflected. And in the polar regions, there is negative heat balance. That means whatever heat is coming, more heat is going back, less amount of heat is getting absorbed. So if it is more than 50%, we say positive heat balance. If it is less than 50%, we can say there is negative heat balance. Now look at this diagram. This is also very interesting. You can see these are latitudes. This is solar radiation watt per meter square. This solar radiation, intensity of solar radiation. What do you mean by intensity? Now see, suppose that light is falling on my palm. The intensity of light beam falling on this palm is calculated on the basis of 2-3 things. Number one, what is the amount falling on it? Amount of energy. Light is a form of energy. What is the amount of energy falling on it? And not only that, if it's a large sheet of, say, newspaper, more amount of energy is falling on it. So instead of energy, we look at the power. How much is the energy falling per second? And not only that, we also take this into consideration, this meter square. In unit area, what is the amount of energy coming and falling in unit time? So it is joules per second per meter square. This is the intensity. Stronger is the intensity. I think you know that in the hotter place we feel that the intensity gets stronger. Same sunlight, same radiation, but the intensity gets more and more and we feel it hotter and hotter. Now, if you really look at it, you will find that lot of heat is, intensity is pretty large at the latitude 0 degree latitude near the equator. But a good part of it is getting absorbed and a part gets reflected by the clouds and then a part gets reflected by the Earth's surface. So ultimately you can see in the polar regions this heat thermal radiation is also less and absorption is very high, so the polar regions really they remain cold and the ice sheets do not melt. So polar regions have got high albedo. Albedo means high reflective power. That's why it happens overall. 70% of the radiation gets absorbed. This is overall. but this is not uniform everywhere, as you can understand. About 30% is reflected back. Now look at it. This is the incoming solar radiation. As I said, 70%, 51% is getting absorbed by the Earth's surface and 19% is getting absorbed by the clouds. What is happening? 30% is going back after reflection. So, with this 30% reflected from the surface is 4%, 20% gets reflected from the cloud. So you can see clouds absorb good amount, they also reflect a good amount, and 6% is reflected by the atmosphere. So altogether 30% goes back overall, and 70% we retain, the Earth retains. Now, what does Earth retain from the solar radiation? What sort of things, what sort of radiation does it get? Well, we get what is known as, we know that, I believe all of you have heard about electromagnetic radiation. Electromagnetic radiation, the very common example is that something, light rays, if you look at our body, we are having quite a few sensory organs. We can pick up sound by our ears, we can pick up smell by our nose, and we can see by our eyes. But remember, we cannot see if this room gets illuminated. For example, say, imagine with the help of X-ray, we won't be able to see the room. This is because eyes are machines, certain instruments. They have got enormous capability, but they have got their own limitations. It will detect only light rays lying in this small part of the electromagnetic spectrum. We call it visible radiation. On the left hand, that means on the shorter wavelength side, it is violet, and the longer wavelength side, it is red. But there are other parts, as you know, infrared is there, mainly used for heating. You have heard about it. And there is ultraviolet. Ultraviolet, you know, that is, there is some, in solar radiation, there is a small part of ultraviolet, a small part of infrared, but ultraviolet is harmful because it's more energetic, they can cause skin cancer, but a good part of ultraviolet gets absorbed by the, what's it called, ozone layer, about 50 kilometers above the Earth's surface. So that way, that protects us from this dangerous ray. And there is, of course, microwaves. Microwaves are not there in the solar radiation, but in the electromagnetic radiation we do have microwaves. Microwaves are when you know, and there are radio waves. And on the other side, on the shorter wavelength side, there are X-rays. X-rays, you know, X-rays are very short and very energetic. If they fall on my palm, it penetrates the flesh and gets reflected from the bones only, so we can take the photographs of the bones. And of course, gamma rays are even more energetic. They come from what is known as, in a nuclear phenomenon, they can be observed. You have heard about that when a nucleus decays, radioactive nucleus, it can give us alpha rays, it can give us beta rays, it can give us gamma rays. Now, and these are a very familiar thing. Velocity is given by nu into lambda, frequency into lambda, and energy depends on the frequency, E is equal to h nu. Now we shall try to take a quick look at the other parts. That's what I mentioned, that our sensory organs, our ears have got limitation, our eyes have got limitation. So far our ears are concerned, you know, we can pick up only sounds of 20 hertz to 20,000 hertz. Nothing beyond that. So that's why when a pendulum oscillates, it takes 1 second. Suppose it takes 1 second. So time period is 1 second, frequency is 1 hertz. We cannot pick up that sound. We can observe it, we cannot pick up that sound by our ears. So it has got its own limitation. Similarly, our eyes, it has also got its own limitation. So it can pick up only the wavelengths of visible light, roughly speaking from 400 nanometer to 750 nanometer, maybe 720 nanometer. Now, these are what are the other parts? Other parts I would like to show you quickly. These are the electromagnetic radiation. This is an invisible spectrum. Invisible means we cannot pick up by our eyes, but they are longest frequency and they are used for radio propagation, audio frequency modulated and amplitude modulated radio frequency is there, and frequency modulated radio waves are there. These are used for radio and broadcasting. Look at the microwave. I think you know that microwave, they all contain invisible radiation. If you have looked at your microwave oven, you must have noticed that you cannot see any radiation passing and falling on the, say, a bowl of water you have given over there. You cannot see you do not know what sort of radiation is coming, because microwaves cannot be picked up by your eyes. But they do exist there. you can understand by looking at it. Once you bring out that bowl of water, you can find that its temperature has gone up. It is hot. So that way, microwave can be used for heating. Microwave can also be used for communication. Different communications, the microwave has an important role in mobile phone communication and other communication. So these are longer wavelengths, longer than the infrared. Now this is also a very interesting photograph. This is what is known as infrared photograph. Now if I use visible light, I can get you a complete picture. But if I use X-ray, well, if I put my hand on palm like this, if you take the photograph, you will get the photograph by visible light. You will get the photograph like this. But if I put it before the X-ray, what will you get? You will get some bones, patterns of that. Similarly, if you really put this palm before the radiation, infrared radiation, you will get this sort of picture. Different parts, different colors indicate different temperatures. That way it's very interesting. You can see that my palm, it doesn't have same temperature all around. You can see the temperature range is 22 degrees Celsius to 33 degrees Celsius. These colors indicate different temperatures at different times. So in the fringes, the temperature is lower. Lower means, of course, there's an assumption. Since these are taken in a cold country, on my arm I keep like this. Suppose you are going down, if you go to mountains, you will find that these areas are colder. But in the central part where the blood circulation is there, it is much hotter. So that sort of photograph will come out. Now, you can see one more thing I must mention, that William Herschel first found this infrared radiation in 1800 AD. I must mention this thing, this is not out of context. William Herschel is a person who found out, who could discover the planet Uranus. And Uranus, so to speak, is the first planet beyond Saturn, about which people didn't know. Uranus, this could be discovered by William Herschel, 1789. Now, this is once again ultraviolet rays. I'm not going into the details that we also divide it into three parts. And ultraviolet A, these are closer to the visible ray. These are very much part of the solar radiation, but of course, ultraviolet radiation is also important. It doesn't really damage our cells. It helps us to, what we call production for the vitamin D. So I'm not going into the details of it. Now this one is a very famous photograph I really wanted to share with you. This is the first photograph, X-ray photograph, and this is the photograph of Röntgen's wife. He really tried to find out that what was really going on, what sort of, once he discovered these rays, and since he didn't know the character of the ray, and he was also not sure whether these are particles or the stream of particles of the rays, he initially called it X-rays. And this is the first photograph of his X-ray taken of the palm of the Röntgen's wife. The very interesting thing happened, you can understand the difference between science and technology over here. Once Röntgen announced this discovery in 1895, it happened like this. Immediately, people, particularly in the USA, and Röntgen was German, he announced it in Germany, but people means physicians and surgeons in England and USA could really see the utility of this thing. They started taking the photograph of the patients, and particularly the orthopedic surgeons. If someone has come up with a broken arm or broken leg, they could immediately take the photograph and could find out what is wrong there, and that really helped them in reevaluating the treatment. So the interesting aspect is that when physicists were arguing, they went on not only arguing, they were doing several experiments to establish clearly whether it's a wave or a stream of particle. The people who really could appreciate its utility, they immediately could apply it for the treatment. And finally, after nearly 20 years, when it was established that X-rays are actually electromagnetic radiation with shorter wavelengths, with more energy, that's why, you know that exposure to X-ray is not good for our health. Then I must mention this, that the name continued as X-ray, so far the British world is concerned, because at that time around 1940, the First World War was on. British really didn't want to acknowledge the German scientists' work, so they continued with the name of X-ray, although X-ray is very much known at that time. But Germans really began to mention it as Röntgen ray. In fact, X-ray photographs they refer to as Röntgenograph. This is another story completely, but not out of context, I believe. Gamma rays, as I've already mentioned, gamma rays come up. You know, how do we get the radiation? In an atom, there is electronic transition. There are electronic levels. One electron goes from one level to higher energy level, gamma means, and when it comes back, it gives out energy in the form of radiation. For X-ray also, this is possible for heavy elements because the energy levels are quite far apart. The energy difference is large. If the energy difference is large, I have shown you H nu. Nu is very large. Nu is large means lambda is small because C is equal to nu by lambda. C is the velocity of light for all the electromagnetic radiation, same. So that way it tells us that we are having shorter wavelength. But we do not get gamma rays in any atomic transition. That is too energetic. We can get it only nuclear transition. When nucleus breaks up, it can give out gamma rays, indicating there are energy levels within the nucleus which are even widely spaced compared to the atomic energy level. Now this was so far so good. Now as you can see, if you have looked at the 7 base units of SI, you will find there is a unit candela that is used for light related issues. So light is very important, so to speak. People had to devise a separate unit for dealing with the light intensity and other things. I'm not going into it, but the important thing is that after all this discussion, you possibly have heard about the quantum theory of light. The question comes, like a question associated with the X-rays. Well, all said and done, whether light is a wave or a particle. Now, all of us know, in the year 1900, Max Planck, the German scientist, he came up with an idea. He proposed an idea that light was maybe taken as particles, flow of particles. They called it quanta of light. And why did he pick up that idea? Because there was some unexplained phenomena in physics. That is what is known as, I should mention the name, black body, spectrum of the black body radiation, that could not be explained with the help of wave theory, which was well established and well accepted. So Max Planck thought about that, well, let us do away with I shouldn't say do away with, let us keep aside this wave theory of light, let us try out something different, and he talked about this quantum theory of light, and he could explain the wave theory, the black body radiation spectrum. But that was really not sufficient to accept that. Only later on, when other things came up, for example, photoelectric effect could be explained. It was explained by Einstein using the photons of light produce free electrons, and Compton effect also, photons of light produce free electrons and photons of lower energy. When all these things happened, then people generally accepted, well, light can be particles. Light, this quantum nature of light was accepted. It need not be a wave also, only it can be particles. But what happened to the wave model? What's wrong with the wave model? Wave model was very much there. What's wrong with it? As you can see, there are several phenomena associated with light that can be explained as a wave phenomenon. Assuming light to be wave, scattering of light. You can see the blue sky because of scattering. That can be explained only if you accept that lights are waves. There is dispersion you are familiar with. There is interference. There is diffraction. This is diffraction photograph. Polarization. All these things are there. Now the question is, if wave theory can explain so many things, but fails to explain certain other things, whereas the particle theory can explain a few things and fails to explain other things, what should be the real character of the light? This was a challenge. Now, gradually people could understand that this was a long, old debate, so to speak. As all of us know, that Newton first talked about the corpuscular theory. He first talked about the light as particles. But the way Newton thought about the corpuscular theory is quite different from the Max Planck's quantum theory of light. But Newton was the first. He talked about the corpuscular theory. That means when some lights are falling on the road here, essentially some particles are coming. He also stated that depending on the size of the particles, we see different colors. But Christian Huygens, who happens to be a contemporary of Newton, he talked about the wave theory. So gradually, wave theory really got accepted. The phenomena we could observe at that time could be explained with the help of wave theory. Now, Later on, of course, as I already mentioned, in 1900, Planck gave us this theory, quantum theory, and Einstein could make use of that for explaining the photoelectric effect. And let me tell you, the most important thing is that Einstein received his Nobel Prize in he got the physics Nobel Prize in 1921. It was announced in 1922. But you will be, possibly you know, but those who know, do not know, may be surprised to know that Einstein was awarded the Nobel Prize. As a general comment was done in the citation, he was a theoretical physicist. Only one word was mentioned in that citation, especially for photoelectric effect, not for any theory of relativity, special theory of relativity or general theory of relativity. That's a different story, but what I would like to highlight is that Einstein was first to really make use of this photoelectric. Okay. Thank you. Though actually he could explain this. Now the question is, some of the phenomena associated with light can be explained with the help of wave theory, where some could be explained only with the help of particle theory or quantum theory. What is the actual character of light? Now that debate went on. People could realize that we'll have to accept both the characters. But how come you give both you make someone as Dr. Jekyll and Mr. Hyde? Later on, when this thing emerged, that wave particle dualism, people could understand that particles can also be wave. Fast moving electrons can behave like waves. Then it was philosophically more acceptable. And remember, this philosophy plays an important role, very important role in the discussion of science. When wave particle dualism was established, people could more easily accept that if particles can be waves, then waves can also be particles. So the argument was like this. So that way we have to accept the light has dual character, and depending on the experiment, it can either show the wave nature or to show the particle nature. Obviously, one question comes up. Then what about the rectilinear propagation of light? That will really come and place before the students when they are younger. Rectilinear propagation is a simplified assumption or simplified version of wave theory. The phenomenon of reflection, refraction, this can all explain with the help of wave theory. But to start with, we really talk about this rectilinear propagation of light. In fact, you can understand some of the things can be very easily explained with the help of rectilinear propagation of light. But let me tell you, that's a simplified version of the wave theory. If the wave is very small, you can understand. If we assume instead of wave, a beam of light is going, that really gives us pretty satisfactory results. Now, as you can understand, there are three types of things happening. When light falls in a dark body, opaque body, light gets absorbed, it gets reflection, mainly transmission in the glass tube, mainly. So absorption, reflection, and transmission is 100%. So light phenomena is composed of these three parts. Similarly, color of the light we observe in different ways, depending on the transparent objects, they give another color, translucent and opaque. They give depending on the reflection and depending on the transmission. Now, and of course, as I have said, that formation of shadows, solar and lunar eclipse, this can all pinhole camera. This can be explained only with the apparently only with the help of rectilinear propagation of light. But as I have mentioned, rectilinear propagation is actually connected with the wave theory. Simplified version of the wave. So you can understand whenever we are talking about a rectilinear propagation, we are essentially getting a simplified version of wave theory. Now, so far I have talked about physics. I being a student of physics, I must admit I do have some bias for physics, but light does not restrict itself to the field of physics only. We have to appreciate the role of light in a very big way in other branches of science. I shall be briefly mentioning about the two branches about which I have got very limited knowledge. Still, I would like to mention them. Number one, as you can see, photosynthesis. Photosynthesis, important photosynthesis, I did not explain to all of you. the plants produce food and we can use the plants as our food. You know how the whole entire chain survives. This photosynthesis. What happens here? As you can see, the carbon dioxide available in that atmosphere and water that is available, that a plant takes to its roots. If they combine in the presence of light. You see, light-induced chemical reaction, we can say, until there is, if there is no light, this reaction cannot happen. So, this reduction, carbon dioxide gets reduced to this carbohydrate, which is glucose, and water gets oxidized to oxygen. So, during the production of photosynthesis, we get oxygen release that helps us, and that way we say that plants are really helping us to keep the oxygen balance. Of course, this can happen only during the day when light is available. And at night, of course, light, they really do not give, this reaction cannot happen and plants do not give away oxygen. So you can see how this light-induced chemical reaction is at the root of the entire plant world, and that in turn helps us to survive. Now, if we really look at it, you see glucose is used up by the plant over here. Sun rays are coming, leaves absorb the sun's energy, the water is coming to the roots, oxygen is produced in the air, oxygen is given away, and leaves absorb the carbon dioxide. So carbon dioxide is going into the system, oxygen is coming out of the system, glucose is getting produced, and that is the food for the plant. So we can say that, and this particular thing, as you can see, this can happen not only with the visible light, this can happen with ultraviolet and infrared light. And as I already mentioned, the visible light is a part of the spectrum which we can see, is part of the solar spectrum, but there are infrared and ultraviolet to some extent. And as you can see, human cannot produce vitamin D without sunlight. As you can see, when sunlight comes and falls over our skin, dihydrocholesterol is being produced, and then chlorocalciferol is being produced. This is vitamin D3. This goes to our liver that produces hydroxyvitamin D3, and it goes to our kidney. That dietary intake also gives us D3 and D2, fish meat and other supplements. So this way, the sunlight, it really helps us for the production of vitamin D. And as you must have heard that in some of the countries, particularly the cold countries where people really cannot come out very much in the outside and cannot have the sun rays, there is problem with this focus on the vitamin D. And there are typical diseases which essentially indicates the shortage of vitamin D. Now, similar thing happens in chemistry. Chemistry, isomerism is the two molecules are connected in this way. The particular bond formation is like this. But light can break up, I shouldn't say break, light can change the bond, and these are known as isomers. The same chemical formula, but different structural formula. These are known as isomers. And this part is known as photochemistry. As you can see, light can really break up bond-forming reaction. There are two molecules separated. Light can be used to get them connected, and the bond is getting formed. Or there is bond-breaking reaction. We can be using light, the bonds can be broken up. So, I'd like to underline, in biology and chemistry, light, the solar radiation, that means the visible and slight part of infrared and part of ultraviolet, they have got very, very big role, and that helps us. And if you really look at laser you are familiar with. Laser is very interesting. I'm not going into the details of laser, but what I would like to say, what happens in laser, light amplified is a simulated emission of radiation. Now, light pulses do come. They come in short pulses. By short pulses, you mean picosecond pulses, femtosecond pulses. Picosecond 10 to the power minus 12 seconds. Femtosecond is 10 to the power minus 15 seconds. Laser, some of the chemical reactions can be carried out with laser lights. And not only that, very interesting thing is that quite often we are familiar with the chemistry that you are giving A and B, getting X and Y. But we do not know what happened in between because we cannot really track down that short time span. But with the laser-induced reaction, those short times can be well documented, and people could see that there are a good number of intermediate compounds that come up, and they are planning to have extract those intermediate compounds and make use of them. So laser has got a very special chemistry, and that's why we talk about femtosecond chemistry, picosecond chemistry. Lasers are being used by chemists in a big way. Not only by the industries, you know its utility in industries, you know its utility in physics, but these are very much used by chemists also. Now I have come to the last stage. I can quickly tell you that this is a whole diagram. Don't pay much attention to this, but the thing is that in some 30 years back, the whatever energy is being consumed, that major part used to go in space heating. Now for the space heating, this part has been reduced. The interesting thing is that for appliances, there was only 24% was used. Now it is using 34.6%. This is just to show how the demand for energy changes, how the use of energy pattern changes. Now, as you can see, that we mostly use electrical energy nowadays. But of course, we convert it into different forms of energy. If you are running a mixer at home, you are using electricity to get the mechanical energy. If you are using a lamp, you are really using it electricity to get light, and so many other things are there. Now, these lights rays, of course, we have had to design more and more efficient light, efficient lamp. By efficient we mean we want that whatever electrical energy goes in doesn't get wasted in producing heat, because we are not interested in getting heat from light. So designs have changed. You have now know about from the filament bulb we have shifted to CFL. We have now shifted to LED. Now, how do we react? Just a quick look. This is the filament bulb. Its lifespan is about 1200 hours. 40 watt, and it gives us the illumination. It comes in terms of lumen, 400 to 500 lumen. But if you really take a CFL that survives for 8000 hours, it takes 12, in comparison to 40 watt, 8 to 12 watts. And once again 400 to 500 lumen. And this LED lamp, this is 50,000 hours, 6 to 9 watts, even lesser than this, and still 400 to 500 lumen. So you can understand we are really using more and more what is known as efficient lighting. We are trying to make the room illuminated, and we want less energy to be wasted. Just this also a comparison. If you have a 400 watt lamp, this is equivalent to 10 4 feet 50 watt lamp, 5.5 125 lamp. These are all from the standpoint of light we are getting, not from the standpoint of energy we are consuming. Otherwise, if you really look at it, a 40 watt lamp that consumes 10 times more energy than an LED lamp, but gives us the same light. So that is important for us. Now, I have so far talked about the efficacy of light. I have so far talked about how light is helping us. But to tell you frankly, light always does not help us. Can you please give an example where light really doesn't help us? You may argue that, bolo.
So light could waste some useful energy which we could otherwise use for other things.
Light can be?
Light can waste useful energy.
Please, you do.
Light can waste useful energy which we could otherwise use for other things.
Yes, that's a good point. And what about you, please?
In the urban areas, because there is so much light, we cannot actually look at the sky properly.
Very good, wonderful. Thank you. She has given a very nice reply. Thank you very much. That is the point. The light is too much in urban areas. We cannot look at the sky, and there is a lot of wastage. If you have looked at cricket matches being played in the floodlight, you could see sometimes this is being shown from the top, or maybe with some drone photograph. There is a lot of illumination. Those we really don't need. That is poor way of designing. Now what happens if you're really looking at a stadium like this? A lot of light is getting wasted. Now the question is, wastage is always wastage, whether you pay the bill or someone else pays the bill, that doesn't matter. Wastage is wastage. Now, that's why we talk about a word, light pollution. Have you heard this word, light pollution? Have you heard this word, light pollution? Light pollution takes place when, so we are talking about so many qualities of light, but it has also the capability of pollution. So you can understand what really happens. And observational astronomy is really suffering from this. Uh, for example, these people, they're trying to see the sky. If the background is very much illuminated, that is very inconvenient. Let me share with you one experience that happened only in the last week. You might have heard last week on the western sky in the evening, we could see the Jupiter and the Venus, then the moon at the same line but much higher up. I tell you one thing, some of my friends send me photographs, fine, I tried to see it from Kolkata, but I couldn't have a good picture of that. But incidentally, I was fortunate enough to move to a place away from Kolkata, which is a village, I should say, and the night sky, there was no light pollution. I myself could get wonderful photographs even with my mobile phone. So this happens. You remember, light also pollutes. Now, the interesting thing is I would like to share a few photographs of this. This is the photograph of Manhattan, New York. You can see how illuminated it is. Now, any feature of the night sky is not available. You cannot see any feature, isn't it? Now, look at this photograph. This is a photograph of, it is of course painting. This is not a photograph. One theory point. This is Hong Kong, northern hemisphere, 22.7 degrees. That means it is close to the what is known as Tropic of Cancer. 20.5 degrees Tropic of Cancer. Now, they have switched off all. What will happen? How will the sky look like if all lights are switched off? This will be the appearance of the sky. Look at this Milky Way that can be shown still like this. So it is 22.7 degrees north, in the northern hemisphere, near Tropic of Cancer. Now, if we move down, more or less stem, in the near Tropic of Capricorn, how will it look like? This is the, can you please put the light off for a while? This is basically dark, so just to have a better idea. Can you please do that? This is Rio de Janeiro, in Brazil, you know, and it is 22.9 degrees south. So equidistant, more or less. I mean, this latitude-wise, longitude-wise, latitude-wise, they are more or less equally spaced from the equator. Now you can see the feature of the sky. This is completely different. So the city is over here. The city, suppose there is a, imagine, there is a huge fog in the city, and otherwise there is no fog and other things. You can see how lovely it looks like. I also like to show you the previous one. Just look at the sky, how brilliant it is. And light really doesn't allow us to see this. And let me go to the previous one also. This is Hong Kong one. This is Hong Kong. So you can see, there are so many features. Even by our naked eye, you can see so many things. And unfortunately, that doesn't happen when there is light pollution. So, I really wanted to share all these things with you. What I have talked about, I should be quickly summing up. Large part of the globe remains dark, you know. In spite of the light, you need more light, so to speak, because illumination, light is still lacking in large part of the world. Visible light detected by our, well, it's a very narrow region. I have talked about the other parts, infrared, microwave, radio waves, and the lower side, ultraviolet, X-ray, and gamma rays. And there are other parts of the electromagnetic spectrum, gamma ray, X-ray, ultraviolet, ion, microwave, etc. Industrial revolution brought so many changes, but the proper lighting could be possible in 19th century with current electricity. Current electricity has got a very big role in the lighting business. I hope you understand. Otherwise, people used to have this lamps and candles and so many other things. So lighting has changed from the 19th century, and biological processes and chemical reactions, they are light dependent. So we talk about the photochemistry and biological processes are also very important. Light is very important for the biological processes. Light pollution is in large cities an example of the improper use of energy. So I virtually end up here. But you know, there are two light festivals in all civilizations. Diwali is very well known to all of us, and this is the Chinese Lantern Festival. If you just go to the internet, you will find there are different light festivals in different parts of the world. Somewhat, of course, Diwali is very huge. Now, in other parts of the world, we know that Even in 10 Downing Street, Diwali is being celebrated. In what is known as American president is also celebrating it in the White House. So many other things are there. Diwali is really very large. But there are other light festivals in different parts of the world. You can have a look at them. So light has got a very special place for all of us. And we know why it is, but if we really go in a deeper way, we will find there are lots of aspects of life we possibly do not remember, we possibly do not recall. So with this, I stop here. Thank you. Thank you very much.
So, students, I hope you have enjoyed the lecture. Yes, sir. So, we are going to take a few questions. Okay? Oh, first.
Sir, I have a question. Since we were talking about the electromagnetic spectrum and there were gamma rays there, why in matter-antimatter annihilation is gamma rays, like, why are they radiated in that phenomenon?
Okay, good. You see, when annihilation takes place, matter-antimatter, it is very common one is the electron-position annihilation. You will find that mass gets converted into energy. So it is 0.51 MeV and 0.51 MeV energy equivalent. It gets converted into 1.02 MeV. If you really look at this energy, E is equal to h nu, you will find this nu is so large, it is coming and falling in the gamma ray. Because that nu is very large means lambda is very small. So if nu lambda is 3 is fixed, 3 to the power 8 meters per second in vacuum. So the energy involved is very large in a photon. Whatever may be its origin, if the photon involves large amount of energy, it will involve small wavelength on very high frequency radiation.
Thank you, sir.
Sure.
Speak your name, class, school.
I'm Ohana Kubilaj from class 8B, the BSS school. I have a question that what is the difference between infrared light and ultraviolet light?
Okay. As we have seen, infrared is, so to speak, beyond red. What we can see by our eye, naked eyes, with diode. Violet starts from shorter wavelength side, red is longer wavelength side. Anything beyond now red, having even more longer wavelength than the red light are infrared. They can be used for heating. You will find some of the equipments are already there in the market, particularly those are being used with the people who deal with sports medicine and other things. They apply them to heal these pains and other things. In household, you have also observed, we really heat up some cloth and put it over an injury to get it cured. On the other hand, ultraviolet is less than the violet, lambda wise less than the violet. That fact is on the other part of the spectrum. Just these two lie on the two sides of the visible spectrum.
I'm Devanjali Energy from class 8B. I had a question. Actually, in many of the books, the reference is different, but it's found that many of the books say that light is a transverse wave, and in another one, like it says that light is a longitudinal wave. So, like what is?
No, let me tell you. What do you understand by transverse and longitudinal wave? Tell me.
So, transverse wave is a wave in which the particles vibrate like perpendicular.
Is there any particle that is vibrating in light rays? Look, sit down, I shall tell you. Can we see light rays are transverse waves? This can be shown with the help of polarization. Now remember, these both of the light rays and sound waves, both of them are waves, but don't mix them up. Sound waves are mechanical waves. Some mechanical vibration has to be there, number one. Number two, there must be a medium for propagation. And number three, the velocity of propagation is much smaller. For the light, there is no particle vibration. Electric and magnetic field, they vibrate. And in the perpendicular direction, there is propagation takes place. That way it is number one. It doesn't need any medium for propagation. And number three, it has got much higher velocity. So these two, I mean, both of them are waves. Just sound waves are mechanical waves which can be picked up by our ears. We can say that these are sound waves. But really, as I told you, if you look at the oscillation of a pendulum, it is also producing a mechanical wave, but our ears cannot pick up. So the general name should be mechanical wave, the general name should be electromagnetic wave, not the light waves only. Please.
My name is Alicia. I'm from AUB, the BSS school. My question is, how does the cloud reflect so much light back when it is made up of water? It should refract the light. And how is it reflected?
Yes, that's a good question. Actually, how they know it is found, you will find, I mean, if you look at it in a different way. Suppose the sky is very cloudy. Don't you find the place is getting a bit colder? It gets humid. It gets to discomfort. That's a different thing. Because the discomfort is a combination of temperature and humidity. But you can see that things get a bit colder. If it is really very dark cloud, it gets colder. So that way, cloud has, yes, what you have said is correct. What happens, these water droplets on the cloud, they are capable of absorbing the light rays, solar radiation, and also part of them they can reflect. So a distinct part is being played by the cloud because of its composition, and we can feel it from the earth in a different way. We do not know what is happening above, but solar radiation that was coming, we can understand. This is immediately a cloud cover, shadow, and the temperature is going down because a lot of light is getting reflected from the cloud. This happens because it's composed of light, water droplets. And you will find also one more thing I must mention, that when solar radiation reaches the surface of the earth, the reflectivity is not the same from the ocean and from the land. These two differ. We are talking about the overall.
Anybody else?
My name is Pratishtha Shaha and I'm from 8A. And as you had mentioned that the X-ray light penetrate deep inside the human body and reflect back from the human bone, why do they not reflect light from the human flesh?
Okay. The reason is very simple. You know, visible light has got, compared to X-rays, much longer wavelength and much much longer wavelength, and its frequency is much lesser. Energy depends on E is equal to h nu. Higher is the energy, higher is penetration power. Gamma rays can penetrate even more. So what happens? Even ultraviolet rays, they are more energetic compared to visible light, but they can really damage your cells on a skin. They cannot penetrate the skin that way. I mean, penetrate beyond that. They cannot penetrate the flesh. Now once you go to the X-rays, X-ray can penetrate the flesh. But if you go to the gamma rays, they are even more harmful. And you must be knowing that we use gamma rays for some medical treatment for cancer patients in a regulated way. They are very much energetic. So it depends all because of energy, and that's why we say that particularly those who are technicians and doctors dealing with the X-ray equipment and other things, they have to be careful. They must put on lead, shielded.
In a place when there is any liquid or gas is there, if you actually
lead shield, and then of course they get protected. Otherwise, continuous exposure to X-ray will really cause cell and tissue damage will take place. This is mainly because of the energy. And you must be knowing, there are two terms. We call about hard X-ray, soft X-ray. Soft X-ray, I mean, X-ray is a range, say roughly from 1 angstrom X-ray that we use and to 100 angstrom. There also each X-ray is not equally penetrating.
So we are going to take the last question today from here.
My name is Aratrika Mitra and I am from class 7C of the BSS school. I wanted to know that since it was said that visible light is detected by our own eyes in a very narrow region, and since our ears can detect the vibrations between 20 hertz and 20,000 hertz, why can't our hearing and seeing abilities extend beyond that region?
Thank you. Thank you. Once again, very good question. It provides me an opportunity to discuss certain different things. Actually, এখানে গুপি গাইন বাঘা বাইন দেখেছো তোমরা? আমরা যখন দেখেছিলাম তো প্রথম যখন তৈরি হয়েছিল ছোটবেলায় আমরাও তখন ছোট ছিলাম, একজন বললো, কমেন্ট করলো, আচ্ছা এত ভালো খাবার দাবার খাচ্ছে গুপি বাঘা, হ্যাঁ খাওয়ার আওয়াজ শুনতে পাচ্ছি, হ্যাঁ খাবারটা খাচ্ছে দেখতে পাচ্ছি, গন্ধটা তো পাচ্ছি না। গন্ধ পাওয়া যায় না কেন বলো তো? Because our sensory organs, they operate in different principles. Until and unless some molecules really enter our nose, আমরা গন্ধ পাবো না। এই অ্যাকচুয়াল ট্রান্সমিশন হওয়া চাই। ও যদি একটা খুব ভালো পারফিউম এখানে ওখানে, যতক্ষণ পারফিউম মলিকুল এখানে না এসে পৌঁছেছে আমি টের পাবো না। সো গানের ক্ষেত্রে কি হচ্ছে তুমি দেখেছো, suppose there's a big ground, look at the Kolkata Maidan. Some people are talking at the one end of the ground. You know they're talking, they're waving their arms and other things, but you cannot listen. They're producing sound. Ki holo? Keno pelam na? That is because of the fact our ears, actually dust can pick up that frequency and she has been 20 kilohertz. But there is a question of intensity. Our কান সমস্ত intensity নিতে পারে না. When sound is coming from a very long distance, its intensity is so poor, our ears cannot detect. But let me tell you, our ears are amazing instrument, amazing. That's why you will be able to find it can really detect intensity as low as 10 to the power minus 12 watt per meter square to 10 to the power 1, just 1 meter per watt square. A range of 10 to the power 12 times. লক্ষ কোটি গুণ ইন্টেন্সিটি সে শুনতে পারে, খুব ছোট খুব বড় শুনতে পারে। আরো তো আবার সীমা আছে, গড়ের মাঠের এক প্রান্তে যদি কেউ কথা বলে সেটা আমি ধরতে পারি না, কারণ এখানে তার থেকেও কমে গেছে ইন্টেন্সিটি। সো কানের ক্ষেত্রে our ears, we need to remember two things. Number one, the frequency is important. Number two, intensity. That is important for all the instruments. For example, if there is an intense light, suppose this light is falling onto my eyes, my immediate reaction is to close my eyes, because I cannot take that much of intensity. If you tell me, sir, whatever light you are getting, a visible light, you can easily see that. No, our eyes can really tolerate up to a certain intensity. The advantage is that we can immediately close the eyes. কানের ক্ষেত্রে সুবিধা হচ্ছে কি, কানটা এত বড় রেঞ্জ নিতে পারে বলে আমাদের নেচার কানটাকে চট করে বন্ধ করার রাস্তা দেয়নি। ও আসুক আমরা শুনে নেবো, হ্যাঁ চোখকে বন্ধ করার রাস্তা নেই। তোমার চোখের উপরে একটা জোরালো আলো পড়লে you always have learned that we should not look at the sun straight away, we should not particularly solar eclipse, we must take proper precaution and that sort of things. So you can understand that all our sensory organs, they are amazing, I tell you, amazing. They can allow us to do so many things, but we have to appreciate what they have got their own limitations. Beyond a certain thing, limit, they cannot do this. Does that answer your question? Thank you.
So, thank you. Actually, we have a taking of time. That's why this is the last question. And now, vote of thanks. A great applause and special thanks from PITM to Dr. Bhupati, a renowned physicist and former HOD of City College, Kolkata. And also I thank the media persons for their valuable presence in the auditorium right now. And the Vice Principal Madam of BSS School to allow you to send us VIPN today, and also Maria ma'am, Suparna ma'am, other teachers, please accept our gratitude to take the day to bring the children over here. And now we're going to watch a film produced by BITM. The name of the film is Characterizing Color, Dr. Sir C.V. Raman at 1. And after this, our today's program will conclude. Thank you, sir. Thank you. Please come. Thank you very much.
Thank you. I really sincerely thank the authorities of BITM for providing me this opportunity, and I sincerely thank all the students present here because of the lesson, and they have asked very nice questions. And I tell you one thing very frankly, what happens, once you raise these questions, we always learn something that, well, I really missed this point. Next time if I talk about it, I must mention it. So it is always a two-way help. I mean, you are really helping us in a big way. Thank you very much. Wishing you all the best. Thank you.